The formal definition of a limit makes it really clear what is necessary for the y values of a function to truly approach a limit L. For this to happen, there has to be a delta for every single epsilon, no matter how small epsilon is. The idea is no matter how close you want your y values to be to L, there always needs to be a range of x values which are close to A, which will yield y values that are close enough to L. So the way we make this formal is that if we say that the limit as x goes to A of fx equals to L, this limit statement here, what it means is that for any epsilon, no matter how small epsilon you pick, there's going to be a delta. Delta is always going to be almost as small as epsilon is. It's going to be usually close to the size of epsilon, such that as long as the distance between x and A, the absolute value of x minus A, is less than delta, then the absolute value of f of x minus L is less than epsilon. There's one part of this definition which is a little bit confusing to some students, which is this part here. The fact that the distance between x and A has to not only be smaller than delta, it also has to be bigger than 0. The reason for this is because if the distance between x and A is 0, then x is A. And we want a statement about a limit to not depend upon the value of the function at the point A. We want it to be talking about what happens around the point A, which is why we want to restrict that distance between x and A to be some number that's bigger than 0 but still smaller than delta. So numbers that are close to A but not equal to A. So if we want to think about this formal definition of a limit graphically, we can think about it with this sort of picture down here. The idea is that epsilon sort of gives you the size of a horizontal strip around the limit value L. So if epsilon equals 0.1, we go 0.1 up and 0.1 down. If epsilon is 0.5, goes 0.5 up and 0.5 down. And the idea is we want to be able to find a delta, we want to find the width of a vertical strip such that as long as our x values are within the vertical strip, the y values will be within the horizontal strip. As long as the x values are within this portion of the graph, the y values will be within this portion of the graph. And again, there's an exception for the value of the function at A. If the value of the function at A is up here, the limit still is L. Having a point up there at the number A does not affect the value of the limit. One thing to mention about this epsilon-delta definition is that the limit value does come into it. Oftentimes people just think about the epsilons as deltas as being related to each other. They're also related to the limit value L. So for example, suppose we thought that the limit as x goes to 2 of x squared was 5 instead of 4. So the idea is we want to show that that statement is not true by showing that there are some epsilons for which deltas do not exist. Right? For the limit to exist, there needs to be a delta for every single epsilon. And for the limit to be a certain value, there needs to be a delta for every epsilon in that limit value. If a limit value is 5, and we've got like limit of x squared, we'll show that there is no delta for example, epsilon equals 0.5. So if epsilon equals 0.5, the idea is we can sort of think about this as we want our y values to be within 0.5 of 5. So here's 5, and we can take a strip between 5.5 and 4.5. And we have here the graph of y equals x squared. Now around 2, the value of f of x is in fact 4. It's actually totally outside of this horizontal strip. So no matter how close we pick our delta to 2, the graph around that point is still going to be outside of that horizontal strip. So the idea is for that epsilon, which is 0.5, there's no delta for which the x value is close to 2 will be within 0.5 of 5. So that's sort of a way of explaining why the limit as x goes to 2 of x squared is not 5, it is actually 4.